Hello, today we're going to cover exact equations. Now this is an optional topic in the course, but it's a method that is extremely important and has other implications in other classes. And so I choose to cover it, but I don't take it as far as the book does. So we will get like an introduction to exact equations and working with the simplest kinds that don't need to be somehow fixed in any way. And that will make more sense in a little bit. So before I can talk about exact equations, though, we have to kind of take a dive through some multivariate calculus. And I realized that multivariate calculus is not a prerequisite for this course. So I'm going to do a quick little mini lesson on what's going on here. So in multivariable calculus, we learned that if we have some variable or some function z, which is equal to some f of xy, and that in turn is equal to a constant c, then the total differential, that's new for us. We've seen derivative, but we have not seen total differential. We've even seen something like partial derivative a little bit. And so maybe start thinking that the total differential is how we put together partial derivatives in order to build a full differential on a multivariate function. So the total differential is the process of taking the differential, not derivative and not partial derivative, of both sides of this equation. And so even though we haven't covered total differential or partial derivatives, I think we can still do this. So here's what I've got. If the total differential is little d, right? When we've taken derivatives, we say d dx. And so differential is just the d. And that d is hitting every variable and saying, what's your derivative? What's your derivative? What's your derivative? And because we've got multiple variables, it wants to not only know what's your derivative, but with respect to which variable. So if I take little d of z, then that is equivalent to me taking little d of a function f of xy, and that's the same as taking a little d of c. So I've got my triple equality, and I'm going to come up with something here. So if I take little d of z, then it's just dz. The derivative of z with respect to itself is 1, and then times dz so that we know that it came from taking the derivative with respect to z. The derivative, little d, the differential of f of xy is twofold. So first it's like, oh, what's your first variable? And then it wants to know with respect to your first variable is x, so let's find a derivative with respect to x, and then let's do the same thing with respect to y. So when we take this total differential, as little d is running through the f of xy, with regards to the variable x, what we're going to get is this first term. And this first term is the partial derivative of f with respect to x, and then times a dx. So when we take the partial derivative of any function with respect to just one variable, the result that we get, it won't be obvious that we just took a derivative with respect to x. It'll just be some function in there. So the dx is like our indicator, right? So we find the partial derivative with respect to x and then dx. And then we run through the function one more time, but now we only consider y. And so we have the partial derivative of f with respect to y, dy, right? So those differentials, dx, dy, dz, they all indicate which variable was affected when little d went through and hit the function. Little d of a constant c is still just going to be 0. So still take the derivative of a constant to be 0. Now, I'm going to do an example so that we can all see, like, how does this whole partial derivative thing even work? Okay? So we're supposed to find the total derivative, and we're going to be using dz is equal to del f del x dx plus del f del y dy. And because we're using this means we first need to find the partial derivative of f with respect to x and the partial derivative of f with respect to y. Okay, so let's calculate those. The partial derivative with respect to x is the same as saying we're going to take del x of, and now I'm going to plug in my f of xy, x e to the 2y minus sine of xy plus y squared. And let's see what we get. Okay, so when del x hits the first term is x times e to the 2y. Now I have to consider that y is just a constant. I'm taking the derivative only with respect to x. Any other variable that shows up, I treat it like a constant. So e to the 2y is like a 7. And if I took the derivative of 7x with respect to x, I would get back 7. So the same thing happens here with our first term. The derivative of x e to the 2y with respect to x is just going to be e to the 2y. Then I hit the second term, the minus sine of xy. And it looks like we've got a chain rule, a little bit of a chain rule here. So I'm going to take the derivative of the outer function, that's the sine. The derivative of sine, of a negative sine, will be a negative cosine. So I get minus cosine of the angle, which is xy, times del x of the angle xy. Right, there's my chain rule coming in. Then plus the derivative of y squared with respect to x. Well, y squared is just a constant. That's nothing right there. Like the derivative of a constant is just 0. So I get plus 0 from that last term. Now the final step is for us to deal with the partial derivative of xy with respect to x. Well, the derivative of x is just 1 and then times a y, so we'll just get a y. So our final answer will be e to the 2y minus y cosine of xy. That is the partial derivative of f with respect to x. Now we do the same thing, but for the partial derivative of f with respect to y. We're going to be sending through a del y to f of xy, which is the x e to the 2y minus sine of xy plus y squared. The first term, the x e to the 2y, the x is just a constant, right? Again, it's like a 7, right? And so if we're taking the derivative with respect to y, we're really focusing on the e to the 2y, which the derivative would be e to the 2y times 2. So the x will stay out as a constant, and then we'll take the derivative of e to the 2y, and then the chain rule will say multiply by a 2. Minus, we're dealing with the minus sine of xy again. The derivative of that with respect to y is another chain rule. The outer function is sine, the derivative, or minus sine, so the derivative is minus cosine of our angle xy times del y of the xy. Next is the y squared, and the derivative with respect to y of y squared is just 2y. And so when we're done, the first term becomes 2x e to the 2y. In the middle term, I still have a derivative to handle. Partial derivative with respect to y of xy would just be x. So my middle term becomes minus x cosine of xy. And then I have I have to fit this in here, plus 2y. Okay? All right, so those are my two pieces. And if I want my differential, I can just pop those in. So we will say, therefore, dz is equal to partial derivative of f with respect to x in parentheses is e to the 2y minus y cosine of xy dx. okay, plus the partial derivative with respect to y of f will be the 2x e to the 2y minus x cosine of xy plus 2y, close the parentheses, and dy. And this is the total differential. So I'd say, it's going to take a little bit of practice to get totally comfortable with this partial derivative thing, but we're not going to be working with anything too cumbersome in this class. If we wanted a differential equation, with f of xy equals x e to the 2y minus sine of xy plus y squared equals c as the solution, that dE would be, in parentheses, e to the 2y minus y cosine of xy dx plus, in parentheses, 2x e to the 2y minus x cosine of xy plus 2y, close the parentheses, dy equals 0. Okay, and these are the types of differential equations we're going to be working with. And we need to be able to work backwards in order to get our solution. And so that's where we're going to start off. Okay, so not every first order differential equation written in differential form corresponds to a differential of f of xy equals c. But in the case where it does, we call it an exact equation, and then we know we can solve it. Okay, so that means we're going to need a way. So we will need a way to be able to determine if an equation is exact. And that's going to require a little bit more theory. Okay, so let's keep going a little bit here. We have a definition. A differential expression, so this is just an expression, m of xy dx plus n of xy dy, is an exact differential if it corresponds to the differential of some function. A first order differential equation of the form where we have that differential expression on the left and then it's set equal to 0, this is said to be an exact equation if the expression on the left side is an exact differential of some function f of xy. But how do we know for sure if we have an exact equation? Because that definition did not actually help to know how we would know. So here's our theorem. We're going to let m of xy and n of xy be continuous and have continuous first partial derivatives in some region. Then a necessary and sufficient condition that m of xy dx plus n of xy dy be an exact differential is that if we were to take the m function and calculate the first partial derivative with respect to y, it would be equal to taking the n function and finding the first partial derivative with respect to x. If we get that equality, then we know we have an exact differential, which means we're working with an exact differential equation. Now here's what's going on. If we assume that m, whatever m is, it's that function that's next to a dx. If we're assuming that m of xy is the first partial derivative of our solution with respect to x, and n of xy is the first partial derivative of our solution with respect to y, then m and n were already first partial derivatives, okay? And so the statement up here is actually the exact same thing as the statement down below here. Now this notation is really weird, especially if you've not taken Calculus 2. The left-hand side says the second partial derivative with respect to x and then with respect to y is equal to the second partial derivative of f with respect to y and then with respect to x. So those are the mixed partial derivatives. If I take a function and I find its derivative with respect to x, that would be my m. Then I take m and I find its partial derivative with respect to y. That is what this guy is on the left, okay? And similarly for the partial derivative of n with respect to x, if n was already a first partial derivative with respect to y, then taking the derivative of it with respect to x now results in the second partial derivative of f, where we took the first partial with respect to y and the second partial with respect to x. Okay. So this comes from a theorem from multivariate calculus. It's called Clairaut's theorem. And basically it states that if you have a continuous function f with continuous first partial derivatives, then the mixed partial derivatives will be equal. So we're using that theorem right now. I'm just going to highlight it because this is where it's all coming from. We're using that so that we can work backwards from an exact equation to even get a solution. Okay, so your job is always to remember that in an exact equation, these two things are true. M is the partial derivative of our solution with respect to x, and n is the partial derivative of our solution with respect to y. Okay, now let's see what the process is for solving these equations. Okay, the process I use is different from the book, but it is just as valid, and to me it's a little bit more direct. The method in the book is a bit circuitous, which means it moves in a circular fashion and you can often get lost in it. So I prefer this method to the book's method, but you are welcome to look at both and do the one that works for you. So since m of xy is equal to some first partial derivative of f with respect to x, then it must hold true that if we were to integrate m, we would be getting back our solution as long as we integrate with respect to x. Since m is a partial derivative with respect to x, you would think that taking a partial integral with respect to x would give it back. But it might have an extra little bit to it. This g of y, that's like our constant of integration. We might end up with like a piece that's just a function of y, and that is our constant of integration, and it's the piece that got lost possibly when we found the partial derivative with respect to x. Next, since n of xy is supposed to be the first partial derivative of f with respect to y, then it must hold true that we could integrate, do a partial integral with respect to y, and get back our f of xy. We'll get a constant of integration possibly, and that constant might be a function of x. And that's okay because the integral was with respect to y, so x is a constant when we're integrating with respect to y. Once we get these results, we'll compare the two things that we found. They're both claiming to be f of xy. So we'll just use them both to help us build what f of xy really is. We'll see when we compare them that there will be some things that show up in both expressions. We just count those one time. And then we might see that one of the expressions has a term in it that we don't see in the other one, We count that one time. And we form our solution from all these parts. There will be times when a differential equation is not exact, but it could be made exact by using a different sort of integrating factor. We are not covering this topic in this class because exact equations are already an optional topic, okay? So we're gonna just learn the basic process. We'll do a few examples on it, but we will not be dealing with any problems where we have to make an equation exact in order to go through with the exact equation process, okay? So here's some examples. Let's get started. Determine whether the given DE is exact. If it is, solve it. All right, we have in parentheses x minus y cubed plus y squared sine of x, all dx, is equal to, in parentheses, 3xy squared plus 2y cosine of x, all times a dy. The first things first is to get into the differential form. And the differential form means that anything that's a function and has a dx or a dy on it needs to be on the left-hand side of the equal sign. Absolutely. So we should see something like an m of xy dx plus an n of xy dy is equal to 0. Notice the plus sign in front of the n. If we have a minus sign, then we need to distribute it to know what our n is. Okay? So I'm going to move everything over. And what I get is, in parentheses, x minus y cubed plus y squared sine of x dx minus, in parentheses, 3xy squared plus 2y cosine of x dy is equal to 0. Now this is not quite in standard form for the differential form, so I need to distribute the minus sign first. So I rewrite x minus y cubed plus y squared sine of x dx plus, in parentheses, minus 3xy squared minus 2y cosine of x, close the parentheses, dy equals 0. Okay, the term or the factor in front of dx, that is my m of xy. The fact that there's a dx in front of it tells me that m of xy would have been possibly a partial derivative of f with respect to x. So the dx is telling me which partial derivative has already been found. And so now I need to find del m, del y. Okay, that way I'm getting a mixed partial derivative. That means I'm going to take del y of x minus y cubed plus y squared sine of x. When I run a del y through there, the derivative of x with respect to y is 0. The derivative of minus y cubed is minus 3y squared. The derivative of y squared sine of x, the sine of x is just a constant, so this will be plus 2y sine of x. Okay, similarly, the term or the factor that is in front of dy, that is our n of xy, and it is thought to be possibly del f del y because it is right next to a dy. So that's how I know which derivative has already been taken. And that's what lets me know that I want to calculate the opposite one. I'm going to take that n and take the partial derivative with respect to the other variable, x. So that means I will run a del x through the minus 3xy squared minus 2y cosine of x. Okay? All right, so the derivative with respect to x of minus 3xy squared, the minus 3 and the y squared are my constant, so I'm focused on the x, and the derivative of that is 1. So this gives me minus 3y squared. The derivative of minus 2y cosine of x, the 2y is a constant. The derivative of cosine is a negative sign, So I have minus a negative, which is a positive, 2y sine of x. All right, let's compare these. I have minus 3y squared plus 2y sine of x. For both, these are equal. I'm very happy about that, because what this means is the equation, or the differential equation, is an exact equation. And that means I can solve it. Okay? All right, so the next thing, and I'm going to shrink this up a little bit so I don't run out of room. My next step is to work backwards in order to get my solution. Okay, so let me see. I got into differential form, and then I want to just label this. The second step was showing that they're exact. So my third step is to go ahead and use the fact that f of xy is equal to the integral of m of xy dx, and f of xy is equal to the integral of n of xy dy, and see what that yields for me. Okay, so the first one, f of xy is equal to the integral of m of xy, which was x minus y cubed plus y squared sine of x dx. All right, so when I integrate, I'm going to send my integral through to each of the three terms. The antiderivative of x is 1/2 x squared. The antiderivative of minus y cubed, that's a constant. And if we integrate a constant, we get back an x times the constant. So I should get minus xy cubed. And then the antiderivative of y squared cosine of x, or sorry, sine of x. I'm saying the answers when I'm trying to read the question. So the antiderivative of sine is a negative cosine. So I get a negative y squared cosine of x, and then plus some possible h of y, where that's my constant of integration. It is in terms of just the other variable. It may or may not be something non-zero. Okay, we'll see. The other option, you know what, I want to do something so that my notes are just a wee bit more explicit. Let's say f of xy is equal to the integral of m dx, which is equal to that. Okay. The other one is and f of xy is equal to the integral of n dy, which will be the integral of, let's see, minus 3xy squared minus 2y cosine of x dy. All right, if I send my integral through all the terms, the first term is minus 3xy squared, so minus 3 and the x, those are just constants. The antiderivative of y squared is 1/3 y cubed, so I get a negative xy cubed because the 3's will cancel out. The antiderivative of the minus 2y cosine of x, we're just focused on the y. The 2 and the cosine of x are constants, and the antiderivative of y is 1/2 y squared, and the half will divide out with the 2, so I just get minus y squared cosine of x, plus some possible g of x, which is my constant of integration. Okay, let's compare things. I'm going to underline the things that show up in both. Minus xy cubed, minus xy cubed. Minus y squared cosine of x, minus y squared cosine of x. And then I'm going to circle what is showing up only once. The 1/2 x squared shows up in the first expression. Okay, so now build f of xy by comparing, not adding, just comparing the two f of xy representations. So what we have is f of xy is each of the things that they share in common. That's true. So we just write each one once. So we just get minus xy cubed minus y squared cosine of x. And then anything that was unique to one of the expressions, that's got to be there too. So we get plus 1/2 x squared, and that's it. This is equal to some c. So we actually do need a constant for a constant of integration. C could have been 0, but we need it there. If we had an initial condition, we could evaluate what C is. But for now, this is the solution or the family of solutions to the exact equation that was given. Okay, we need another example. We're going to determine whether the given DE is exact, and if it is, we'll solve it. And the very first thing we have to do is get this in the standard differential form. This is so not in the differential form, and seeing the dy over dx can be misleading when you're working through this problem. So the very first thing we have to do is split up those dx's, the dx from the dy, but also all those terms, I've got a plus y is equal to 3 over x minus a 1. I want those all together, okay? So maybe I'm going to move over the 3 over x and the minus 1 first. So when I rewrite, I want to get into differential form. And just in case you forget, that's the form m dx plus n dy. And technically equals 0. Okay, so we have 1 minus 3 over y plus x all times dy over dx plus y minus 3 over x plus 1 equals 0. We're still not there. I need to split up my dy and dx. So I'm going to multiply the last 3 terms by a dx. And so I get 1 minus 3 over y plus x all times dy plus, in parentheses, y minus 3 over x plus 1 all times dx equals 0. Now notice that these are actually in the wrong order. I have the dy first and I have the dx second. That's not a problem, but it can mess with you in your homework. So we really should have things in the right form where the dx term comes first. So one more rewrite, y minus 3 over x plus 1 dx plus, in parentheses, 1 minus 3 over y plus x dy is equal to 0. Now we're in differential form. The factor in front of dx, that is our m, we have an assumption that it is possibly del f del x, the partial derivative of f with respect to x. And in front of dy is our n, and it is possibly the first partial derivative of f with respect to y. And so we need to determine if we get mixed partials that are equal first. So we're going to do our exact check. So we're going to check for exactness. That means we want to show that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So let's calculate those. Del m del y is equal to del y of y minus 3 over x plus 1. When I take the partial derivative with respect to y of each of these terms, I get that this is equal to 1 minus, so derivative of y is 1. The derivative of 3 over x is, with respect to y, is 0. The derivative of 1 with respect to anything is 0, so I just get 1. That's it. Del n del x means we're taking del x of our n, which was 1 minus 3 over y plus x. And when I take the derivative with respect to x, The derivative of 1 with respect to x is 0. The derivative of minus 3 over y is minus 0. And the derivative of x with respect to x is 1. So let's just compare these. I get 1 and 1. These are equal. And so we have an exact differential equation. And that means we can solve it. Okay, so what we want to do is use the fact that f of xy is equal to the integral of m dx. So it's a partial integral. We're going to take m. Since m is supposed to be a partial derivative with respect to x, let's partially integrate it with respect to x and see what we get. And f of xy is equal to the partial integral of n with respect to y. So let's calculate those to come up with f of xy. Okay, so f of xy is technically going to be the partial integral of m dx, which means we are integrating y minus 3 over x plus 1 dx. And when I integrate this all with respect to x, the antiderivative of y becomes xy. The antiderivative of minus 3 over x becomes minus 3 ln of the absolute value of x. And the antiderivative of 1 with respect to x is plus x. And my constant of integration is some h of y. Okay, and f of xy is equal to the integral of n dy. And so we're going to integrate n, which is 1 minus 3 over y plus x with respect to y. The antiderivative, as we run through, we're taking the antiderivative with respect to y of 1, which will give me y. Of minus 3 over y will give me minus 3 ln of the absolute value of y. And of x will give me plus xy. And then plus some possible constant of integration, g of x. All right, let's go through and underline what's common to both. An xy shows up in both of these, and that's all that's common. What's different is the minus 3 ln of x, the plus x, the y, and the minus 3 ln of y. So I have to make sure that those show up in my full formation. So when we compare the two representations, we can build f of xy. So f of xy will be comprised of the thing that they have in common, which is the x times y, plus all the individual parts. So I get the minus 3 ln of the absolute value of x plus x, and I get the minus 3 ln of the absolute value of y plus y. And that is all equal to some c. There are ways that we could rewrite this so that it's a little bit more concise using natural log properties, but I'm not actually worried about it. I will leave it as written. It's the simplest way to handle it. And this is going to be our family of solutions to the given exact differential equation. Okay, let's do one more example so that you're all set to get started with your homework. All right, so this one did a similar thing where the dy is with its dx, and so we need to be able to split those up. Everything is to the left of the equal sign, and so I'll just start off with multiplying everything by a dx to get into the exact differential form. And that's the m dx plus n dy is equal to 0. So to start with, I have in parentheses 2y minus 1 over x plus cosine of 3x dy plus, and then I'm going to multiply the next three terms by the dx. So I'll have in parentheses y over x squared minus 4x cubed plus 3y sine of 3x all times dx is equal to 0. And now these, again, they're written in the wrong order. I need the dx term written first, so I'm going to swap the places. And when I rewrite in parentheses, I have y over x squared minus 4x cubed plus 3y sine of 3x all times dx plus, in parentheses, 2y minus 1 over x plus cosine of 3x all times dy is equal to 0. On the left, with the dx, is what is possibly the partial derivative with respect to x, also known as m. And the term that's with dy, that is our n, and it is possibly equal to the first partial derivative of our solution with respect to y. And I always say possible because this might not be an exact equation. We have to check. So that's our next step. We're going to check for exactness. And that means we want to show that del m del y is equal to del n del x. Okay, let's calculate them. Del m del y means we are going to take del y of m, which is the y over x squared minus 4x cubed plus 3y sine of 3x. The derivative with respect to y of y over x squared is just going to be 1 over x squared. The derivative with respect to y of minus 4x cubed is minus 0, because that's just a constant. And the derivative of 3y sine of 3x, I really just focus on that y. So the derivative of y is 1, so this will be plus 3 sine of 3x. Now we look at del n del x. So we'll send a del x through to n, and n is 2y minus 1 over x plus cosine of 3x. So we're taking the derivative with respect to x of 2y. That's going to give us back 0. The derivative of minus 1 over x will be a plus 1 over x squared. So things are looking good so far. And the derivative of cosine of 3x is going to be minus 3 sine of 3x. Wow, these are like super, super close, but in del m del y, I have plus 3 sine of 3x, and in del n del x, I have minus 3 sine of 3x. These are not equal. And so this is not an exact equation. And we cannot solve it because we are not going to learn how to. We could solve it. There are methods for solving it. But that's not where we're going in this particular course. We just want to get our feet wet, see what exact equations are and how to handle some very basic ones. It was never about the hardest ones, just the basic ones. So your job and homework is to be able to, number one, show that you're working with an exact equation or not. And if you are, then you're to work backwards and find your solution, f of x, y. If you have any questions, please feel free to reach out.